All right, so let's talk about deep neural rejection, which is a simple and powerful defense against these attacks. And it's just, what you do is you just do what a human would do. You find the images that look funny and you throw them out. But you can automate that. So this is deep neural rejection. You have a model. So on the left, you see a neural net processing an image through several layers of neurons, sort of described here, and then it'll separate them into categories. So imagine that we're sorting input images into, say, categories 1, 2, and 3. And these are support vector machines that assign a class score. So you end up with, and then you make a classifier, and what it does is it combines these to a single score, which is just a single measure of the general shape of the image. And now you find the ones with this score that are far away from the range of acceptable ones, predicted outputs, and these are the ones that look funny. So it's going to learn what features are best for this, but it's just going to measure some facts about the data and boil it down to one measure of how funny looking it is, and the ones that are too funny looking, you throw them away. And this turns out to be plenty effective as a defense. So let's see, let's set this up. Here's the training set, which is going to be the MNIST data again. Those handwritten letters that came from, I think, the US Census. And we'll view the first 20 images. Wait for that block to finish. All right, it's downloading the images, getting ready to go. All right, it's got my training set. 1,000 images, 784 pixels per image. And here's what they look like. Okay, same stuff we've seen before. There's the first 20 images with the correct label on them. All right, so now the unprotected deep neural network model is going to be here. All right, and so here's the images. You can see them up here. The first one is 7, the next one is 2, the next one is 1. So here's the correct score. Here's the prediction. So it's image, prediction, correct. The first image is predicted to be a 7, and it is a 7, and so on. And here's the score. Remember, the way this works is you have 10 output neurons, and the signal there gives you a measure of how likely it is that that's the answer. And so you see here, there's a lot of negative numbers, but 4 has a plus 500, 7 has a plus 5,000, and 9 has a plus 270. So 7 has the largest output, so this is classified as a 7. And we might be able to find one. Here's one that's misclassified. It thought it was a 6, but it should be a 5. So a 6 is here. It had 1,100 signal on 6 and only 700 signal on 5. So that was a mistake. And might be another mistake you find. Yeah, here's a 5. It thought it was a 5, but it was really a 3. You can see 3 had 712 and 5 had 730. So it was pretty close. But that's how it works. You have these output signals, and it chooses the largest signal. And most of the time it's right, but not all the time. All right. So now we're going to attack that model. It's going to train evasion images from the first 20 models. So this is not poisoning the training data. This is creating images which are modified so that it's hard for the model to classify them. Or indeed, so the model will systematically classify them wrong. Again, using an intelligent attack that has access to the model and can carefully choose what changes will do that, what changes will maximally harm the model's ability to classify. And we should see results here. And it's going to look like this. We're going to see the first 20 images and the predicted classifications above them, and you'll see that they're all wrong. Here we are. So this 7 is interpreted as a 0. This 2 is interpreted as a 0, and you can see I've added a little bit of noise to it. Is what the model did, and that's enough to confuse it in all these cases. So all of the first 20 are predicted. All 20 are successful evasions. All 20 of these images are now incorrectly classified by the model. So that's the problem. That's the vulnerability. Our large learning, our not large learning, but our machine learning model is vulnerable to this evasion attack. A little bit of snow added to the image is enough to make it get the wrong answer. And we'd rather have a stronger model that is not subject to that weakness. So we're going to train the deep neural rejector. This is the auxiliary model that will detect when images look funny and refuse to classify them. And it's going to set the reject threshold so it will reject the 10% outliers of the samples. Reject 10% of the samples, the ones that look funniest. And now, the one including the deep neural rejection feature is harder to poison. Of course, that is the point. So now we're going to see how effective that defense is. So I'll wait for this to finish, and then I'll run the next one. It's the step that's taking a while is the fit, of course. That's going through something like gradient descent to optimize the defense here. And, if it's taking too long, I'll just look at the previous scores. So now you find it now has a new option. It rejects certain ones. So now this is on the first 20 images. Now some of the unmodified images are rejected. It refuses to classify them, deciding that they look funny, and that was expected. And then we're going to prepare attack images. So let's get down here. Okay, it's still running. All right. So it takes longer to train this more complicated model with a defense. But it shouldn't take too long. Yep, and when it's done, it's going to find the reject threshold and set it to minus 0.96. Having decided what threshold it will take to reject 10% of the images. All right, it's done, minus 0.96. So that was all done to design the deep neural rejector and adjust its threshold. So now we can see on test images, I think these are training images, a TS set, that's the test set. So now here comes the test set. And you see it's classifying them correctly, but a few of them it refuses to classify. And it decides to reject them, and it's supposed to reject 10%, and it looks like it rejected 3 out of the first 20, so that's pretty close to 10%. All right, and so now we prepare attack images for this model, which is, to be fair, we don't just use the previous attack images, we train new attack images specifically to attack that model, doing the evasion on the deep neural reject model, because that's the point. you make this model, and even if the model is publicly known, this attack strategy is going to be less effective. That's the whole point of the defense, of course. So this will make evasion attack images, 20 of them, and then show us the images, and then show us how well they are succeeding in confusing the model. And anyway, I'll go to these. There's the answer you're going to get. Again, you have similar looking evasion images with a little bit of snow added to them. And now only 6 of them were successful at evasion. Before, all 20 of them were evaded. And you can see the prediction is frequently -1, which means it rejected these images. So it rejected a lot of them, and only a few of them were successful evasions. So that just shows how effective the defense is. You went from 20 out of 20 being misclassified to only 6 out of 20 being classified, and the rest being rejected as unacceptable images. So that's a pretty good defense. And then there's various flags defined by putting modifications of it. So that's what I wanted to show you.